I thank you all for watching my videos all these years. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of June 2023. The question is from the section Real Analysis and it is related to a real valued function on R square. And this question is from the part C, which is a multiple select question, and there can be more than one answer, and it carries 4.75 marks. The question ID is 704068. This question is suitable for all these examinations. Right. The given question is, consider the function f from R square to R, where R is the set of real numbers, defined by f of the ordered pair x comma y is equal to x square minus y cube. Which of the following statements are true? We are given four options. Option 1. There is no continuous real valued function g defined on any interval of R containing 0 such that f of x comma g of x is equal to 0. Option 2. There is exactly one continuous real valued function g defined on any interval of R containing 0 such that f of x comma gx is equal to 0. In option 3, it talks about differentiable function. Option 3, there is exactly one differentiable real valued function g defined on any interval of R containing 0 such that f of x comma gx is equal to 0. In option 4, he talks about exactly two differentiable functions. Option 4, there are two distinct differentiable real valued functions g defined on any interval R containing 0 such that x comma gx is equal to 0. Let's now discuss the solution of the problem in detail. We have the given function f from R square to R defined by f of x comma y is equal to x square minus y cube. Let y is equal to g of x be any real valued function such that f of x comma gx is equal to 0. G of x is, we have given freedom for g of x. It is any real valued function. This implies x square minus y cube f of x comma gx is equal to 0 means x square minus g of x whole cube is equal to 0, which will imply g of x whole cube is equal to x square. Therefore, g of x is equal to x to the power of 2/3, 2 by 3. So, g of x exists. G of x exists, and we have given freedom for g of x. It is any real valued. It comes out to be g of x is equal to x to the power of 2 by 3. So, by this argument, there is exactly one real valued function g of x such that f of x comma gx is equal to 0 and g of x, x to the power of 2 by 3 exists on whole of R on the entire real numbered line. So this shows that there is exactly one real valued function g of x is equal to x to the power of 2 by 3 on any interval of R such that f of x comma gx is equal to 0. Agreed. So what about its continuity? What about its continuity? And note that g of x is equal to x to the power of 2 by 3 is continuous on any interval of R. Right. So what is that we have proved? This shows that there is exactly one real valued continuous function g of x is equal to x to the power of 2 by 3 on any interval of R such that f of x comma gx is equal to 0. Now let's look at our option 1. Option 1 says there is no continuous real valued function g defined on any interval of R containing 0 such that f of x comma gx is equal to 0. So there is exactly one real valued function we have already seen on any interval of R. So it is true on any interval of R containing 0 also. So the option 1 says there is no continuous, but we have exactly one continuous function. Therefore, option 1 is not true. What about option 2? There is exactly one continuous real valued function g defined on any interval of R containing 0, yes, such that f of x comma gx is equal to 0. Yes, option 2 is true. Thus, option 2 is true and option 1 is not true. We continue the discussion in the next slide. So, we have proved there is exactly one real valued function g of x to the power of 2 by 3 on any interval I containing 0 such that f of x comma gx is equal to 0. Further, this g of x is a continuous function. Now, we talk about its differentiability. Differentiability at x to the power of 2 by 3. It's well known. It is differentiable everywhere except at x is equal to 0. So we talk about differentiability of g of x at x is equal to 0. Limit x tends to 0 of g of x minus g of 0 by x minus 0 is limit x tends to 0, g of x is x to the power of 2 by 3, g of 0 is 0 by x. And that is limit x tends to 0, 1 by x to the power of 1 by 3. And the limit, this limit does not exist. As it is sitting in the denominator x to the power of 1 by 3, it does not exist. You can show by means of left limit, right limit concept also. But this is very well known now. So this means g of x is equal to x to the power of 2 by 3 is not differentiable at x is equal to 0. So this implies g of x is equal to x to the power of 2 by 3 is not differentiable on any interval I containing 0. Because of this 0 is there in I. On any interval I containing 0, it is not differentiable. And this means there does not exist a differentiable real valued function g defined on any interval I of R containing 0 such that f of x comma gx is equal to 0. This is our conclusion. Look at our option 3. There is exactly one differentiable real valued function. There is no differentiable real valued function. Therefore, option 3 is not true. Option 4. There are two distinct differentiable real valued functions. There does not exist a differentiable real valued function. Therefore, option 4 is also not true. So, thus options 3 and 4 are not true. The answer to this question is option 2. The option to this question is option 2. That is the detailed discussion of the solution of the given problem from the section real analysis, which is related to a real valued function on R square. Agreed. And this question is definitely a very, very easy, simple, straightforward question. I am sure all of you might have worked out this problem in the examination. I am sure that you have understood the solution of this problem. I thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again for another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.